Hello everybody, let's continue the example of last time and this time introduce the concept of graphical load line analysis. So let's draw the transistor we had last time and with the resistors around it. So we had, that's a little bit too high. Okay, it's okay. We had 10 volts here. We had a 10 volt source here. Then we had a resistor. We had a 100 ohm resistor here. Continuing down, there we had our transistor itself, the collector, the base, and one more. There we go. Here we had the emitter, and below the emitter we continue down to ground. So this was our ground, and then here on the side we had one more resistor. In this case, we had a 2000 ohm resistor. We had a 2K ohm resistor. And we've had a voltage source of 2 volts. We continued here and we had a voltage source of 2 volts. And our findings were that VCE is 3.5, VBE is in the active region, so VBE is 0.7 volts. IB was 6.5 10 to the minus 4. IC was 100 times that, was 6.5 10 to the minus 2. 6.5 10 to the minus 2. Those were our findings. And let's see how we can draw them in what is known as graphical load line analysis. So the first part is easy. I'll just pick a different color. The first part is easy, is just to draw the VBE, IB versus VBE, so that we've seen before already. So here on the y-axis we have IB, on the x-axis we have VBE, and then the VBE is 0.7, then we can, in a simplified version of this, we can say that when VBE is 0.7, IB can take any value we want, and in our particular case, we saw that because of the resistors, because it has to complete the Kirkhof laws, and of the resistors, and because it has to complete the Kirkhof laws, we saw that it takes the value of 6.5 10 to the minus 4 amperes. So it took this value. Yep, in the more complicated analysis, which we don't really have to do, we saw that there was actually like a curve, like there was a curve that goes like this, and then at any particular voltage, there is only one possible value of IB. But, right, so at 0.7, there is only one particular value of IB. So it's more complicated this way. But in the simplified analysis, we can just say that when VBE is 0.7, IB can take any value. The current can be any current. When VBE is 0.7, it's not limited to any particular value. So usually that's how it's done. Usually it just says, look, if VBE is 0.7, IB can take any particular value, and the value it takes is based on the Kirkhof law, based on 2 volts minus 2K ohm times IB minus VB equals to 0. That's the Kirkhof voltage law, and then you find the value of IB. That corresponds to VBE times is 0.7. Okay, that was a little bit of extra. But here's now the important part. The important part that we only saw a little bit of that. The relationship between IC, I did something stupid. The relationship between IC and VCE. So we saw already, and here there was a part that we saw and a part that we haven't yet seen. So here's the part that we saw. The part that we saw was that, let me just, that's roughly 0.2 here, and then just continues flat. So this is the part that we saw. Why? I'm accidentally dragging it. 1 second. Okay, there we go. And then this guy need to be erased. Okay, and then okay. So here the part that we saw was that when. Oh, that's not exactly. Okay, sorry, I'm dragging. Never mind. Is that when this is 0.2, this is the cutoff between saturation and active state. And sorry, I got a little bit of a delay here because of all the little thingies, but okay, let's just finish this one. Okay, and then let's go. And we saw that this curve, all this pinkish curve represents one particular value of IB. In this case, it represents 6.5 10 to the minus 4. So all the values of the pinkish curve, not just the end of it, but everything, the entire pinkish curve, sorry, the entire pinkish curve represents one particular value of IB, namely 6.5 10 to the minus 4. So everything, including the beginning, including everything, it represents 6.5 10 to the minus 4. IB is equal to that much. So not just the end of the curve, but even the beginning, even where it slopes here, where it slopes at less than 0.2 VCE, it still represents one particular value of IB. And then what we saw that we've had VCE is equal to 3.5, was roughly right here, 3.5 volts, and then VCE was here, and at levels above 0.2 volts, we know that IC is going to be more 100 times IB, and that value of 100 times more is just 6.5 10 to the minus 2 ampere. That's the value of IC. And you see the curve here is flat. So IC is going to be 6.5 10 to the minus 2 IB whenever VCE is greater than 0.2. Very well. So we've got that much. Now here is the new introduction. Here is the new item that's a little bit new. There is such a thing as called the load line, and it represents the possible values that VCE can take, the possible values that VCE and IC can take. What is meant by that? Okay. We have 10, let's do the equation. We have 10 volts minus, this is actually a nice color, minus 100 ohm times IC minus VCE equal to 0. So let's write the equation IC as the y in the y-axis and VC as the x-axis. So we have IC equals to minus VCE over 100. And we also have plus 10 over 100. Which is 0.1. Okay, so that is not based on knowing anything about transistors. This equation is called the load line equation. and it just says, look, I need to complete Kirchhoff's law. I know that much. I know that 10 minus 110 minus 100 IC minus VC has to be equal to 0. So I know, what I know is that I have to complete, sorry, I have to complete the Kirchhoff equation. And I just know that very well. And so we see that we need to complete the Kirchhoff equation. So what values of IC and VCE would complete the Kirchhoff equation? So by solving here, we see that I can pick any value of VCE and that it would tell me what is the value of IC that completes the Kirchhoff equation. So let's, for example, now it doesn't matter if that value of VCE is true or not. It doesn't matter if the value of IC is the real value of not or not. It just says, look, pick a value of VCE. I can tell you what is the value of IC that completes the Kirchhoff equation. So let's pick VCE equals to 0. I'm just picking VCE equal to 0. Now, what will be the value of IC that completes the Kirchhoff equation? IC will be 10 over 100, which is 0.1 ampere. Very well. Let's pick another one. Easiest to pick the edge cases. Let's pick IC equal to 0. Let's pick, right, so this is one case. The other case is IC equal to 0. Very well. IC equal to 0. Now, what is, in that case, the value of VCE? To complete the Kirchhoff equation, unfortunately, I write right here, so let's just continue right here. The value that completes the Kirchhoff equation in that case is, I'll just write VCE over 100. I move that to the right side, equals to 10 over 100. Right, so IC is equal to 0, and then I move this one to the left, and then I move this one to the left, and then VCE is equal to 10. Now, does that make sense? This is actually this is possible to see intuitively. Look, if VCE is equal to 10, if this gap is equal to 10, then I don't need any current. 10 minus 10 volts is 0 without any current. On the other hand, if the gap VCE is 0 and I want to go from 10 to 0 and VCE does not help me, if VCE happens to be 0, if the current, it needs to be 0.1 ampere. Why 0.1? 0.1 times 100 ohm, 0.1 IC times 100 ohm reduces me to 0, even, and VCE does not contribute anything. VCE is 0. Okay, hopefully we can see that. So, let's write it down one time. So in the first case, we had, what does it work? 10 minus 100 times 0.1 minus VCE, which we saw is 0, we chose to be 0, is indeed equals 0. Why does the second case work? 10 minus 100 times 0, 100, because we chose IC to be 0, minus VCE, but what is VC? VC is 10. And so VC is 10, and so indeed, the Kirchhoff law works. 10 volts minus 10 volts VCE, 0 current, we go down to 0. So we chose IC, we chose either IC or VCE, And we get if we chose IC, we get the VCE that completes Kirkhof law. If we chose VCE, we get the IC that completes Kirkhof law. Now, it doesn't matter if the transistor can really take that value of voltage. It doesn't matter if the transistor can really take that current. What we're saying here, right, so that's actually the key point. It doesn't matter whether the transistor can really do it. What we're saying, hey, let's find possible values of IC and VCE that would complete Kirchhoff's law. That would, right? It doesn't matter whether the transistor can really do them. Let's just find possible values that would complete Kirchhoff's law. Okay, and now let's add the load line to the main curve. Now it's a little bit tricky because unfortunately I would have to redraw the bottom curve a little bit because I draw it a little bit too big. Okay. Let's unfortunately we might have to do some rearrangements here. That's a little bit unfortunate because there is no space, and unfortunately let's erase this. This is a little bit because otherwise there is no space at all to do all that stuff. This is good, but even this has too much other stuff here, so okay, let's erase it, I suppose. Why have I done? No, the zoom has to be 100. A little bit of technical. Okay, let's just erase this. Sorry, just to clear some space, and one last erasing here and one more here, last one here. Okay, okay, now we have plenty of space to do the same thing. Okay, and these are the values of, now these are the values of IC. These are, of course, in the y-axis we have IC, not VCE. So okay, we have IC, and here in the x-axis we have VCE. And now let's draw the load line. We remember that we had 10 VCE equal to 0, and the other value is that when IC 0.1, let's do it here, IC 0.1, 10 VCE is equal to 0. And that's the load line. Okay, turned out actually pretty nicely, if I can give myself a compliment. Okay, so this is okay. And then we had the real situation. The real situation was that IB was equal to 3.5 volts, and that's the real situation. And then the real IC was 6.5 10 to the minus 2, right? It was 6.5 10 to the minus 2. I'll just write it here, I guess. So just, what is 6.5 10 to the minus 2? It's 0.065. Very well. 0.065 ampere. And here it meets the load line. Then we had IB. Then we had the particular value of IB was, okay, so let's say this is 0.2. And this is 0.2, and then what we have is that it's supposed to go pretty like this, and then from 0.2 it more or less is a straight line. And then this is the value of IB equals to 6.5, 10 to the minus 4. And also intersects here. So now we see we have 3 intersections. Sorry. One intersection is IB is 6.5, 10 to the minus 4. That represents the yellow curve. And we know that IC has to be 100 times IB. So indeed, IC is 100 times IB. And that happens when the voltage is 3.5. So the voltage is 3.5. IC is indeed 100 times IB when the voltage is 3.5. But now we also know that Kirkhof law has to be satisfied. So this point where the VCE is 3.5 volts, this point where VCE is 3.5 volts and IC is 0.065 has to also satisfy the Kirkhof law. The blue line, the blue is the load line, is all the points that satisfy Kirkhof law. The blue line is all the possible points that satisfy Kirkhof law. So this is, now, whether the transistor is there or not, it doesn't matter. The blue line says, look, these are all the points that could satisfy Kirkhof law. If they don't even satisfy Kirkhof law, forget it. So that's the minimum. And the real point has to both satisfy the Kirkhof law, so it has to be on the blue line, and it has to satisfy the transistor conditions. And indeed, that's that point. That's the kind of the real point. So it's on the blue line, but where on the blue line? So where on the blue line? Well, it's on the blue line where it intersects with where it both satisfies the blue line, it's a point on the blue line, and also satisfies the transistor characteristics, namely that there is certain IB, namely here it's 6.5 10 to the minus 4, and there is certain IB, and IC is 100 times IB, and the voltage has to be the particular voltage, where IC is 100 times IB, so this particular voltage here, as long as it's bigger than 0.2, IC is going to be 100 times IB, but this particular voltage is also one that satisfies Kirkhof law. So at a voltage of 3.5, IB 6.5 10 to the minus 4, IC 0.065, both the transistor characteristics are satisfied, but also the Kirkhof law is satisfied. The Kirkhof law is satisfied. So let's see the counterexample, last little bit. So let's say I said, look, let's say the voltage, let's say an imaginary voltage of 7. I say, well, why can't I want it to be 7. What's wrong with that? I say, oh, the voltage is 7, very well. 7, let's not, why not that? Why not 7? I say 7, very good. 7 is bigger than 0.2, or that's it, 0 is bigger than 0.2. Why not? IB is IB, IC is IC. Well, because it's a flat line, IC is going to be still 100 times IB. So IC is still 100 times IB. I see this green line. Oh, I go here, a green line, that's fine. IC is 100 times IB. There we go. IC was just 7. We have IB, and IC is 100 times IB. Why is this not a possible case? Because this case does not satisfy Kirkhof law. Because this case does not satisfy Kirkhof law. The blue line tells all the cases that in fact satisfy Kirkhof law. And this case is not the problem, is not the transistor. Transistor could have this. Transistor could have 7 volts and IB and IC. The problem is not that the transistor is not happy. What's not happy is that this condition is outside the blue line and therefore does not satisfy Kirchhoff's law. So the real point has to both satisfy the transistor characteristics and Kirchhoff's law. And we see that 3.5 volts is on the blue line, so it satisfies Kirchhoff's law. It's bigger than 0.2, so IC is 100 times IB. The transistor is in the active state, and all is well with the world. Like, all is well with the world. That is, all the conditions are satisfied, and the load line in the transistor matches the load line. So indeed, drawing that blue line, this sort of blue line here, of all the possible values of IC against VCE that satisfy Kirchhoff's law, is called the load line analysis. Very well. Great. So hopefully it was helpful in understanding the load line analysis a little bit. Thank you very much for watching the video. All right, I'll stop here.